Hey, we're going to talk about calculating arc length using calculus. So let's see what we've got here. So we can do this by doing the same thing we did when we tried to find the area under a curve. Remember we made like a billion infinite little rectangles and added them up? But in this case, what we're going to do is because we're looking for a length, we're actually going to make like a lot of triangles. So we're going to take a curve and we're going to divide it up into little sections and make little triangles out of it, however you see that happening here. And we're going to do that by having the difference in 2 points, which will give us like the two legs of a triangle. So what we're going to be doing is adding up tiny hypotenuses across here. Okay. Now looking at the way it is, if the hypotenuse or the triangle has any size to it, then definitely it's not accurate. But when you make those points infinitely close together, minimize the distance between them, and get an infinite number of triangles there, those hypotenuses become so small they're the actual length. So let's just kind of think about what those hypotenuses look like. Remember that we can find a hypotenuse if we know two legs by using the Pythagorean theorem, a squared plus b squared equals c squared. So I've got a formula down here that we've got is 1, which will be kind of like the left to right version here. Okay, so we're moving 1 over. And dy dx. Okay, dy dx is a change in y. That's a slope. Well, that slope is an up over, so that is the distance here. So this differential gives me a change in the height. So basically I've got an a squared, which is 1 squared, plus a b squared, which is the height differential here squared, equals the arc length s squared. So that's an a squared plus b squared equals c squared just in itself, and the s here is representing the hypotenuse. So if I want to get that s completely by itself, I'd take the square root. So one of these little tiny triangle hypotenuses would be equal to 1 plus, the square root of 1 plus dy dx squared. Okay, so we're just getting a lot of little hypotenuses there. So what do we need to do? We need to add those up. So here's the same formula. You can look at it a couple of different ways. 1 plus f prime of x squared under a square root. That's exactly what we just had. So that's just going to take and find a little hypotenuse, but then we're going to integrate that from 2 endpoints, and that's going to give us all those hypotenuses added together. So that's the integral, which would give us the length of the arc, or the length of the line. So if we want to write things in terms of x, then everything needs to be in terms of x, including the integration. Or we could write things in terms of y. And this is not dependent upon orientation, per se. It's not like when we did the rotations, we're looking at the x-axis, y-axis, or lines like that to make a decision which one to use. We're probably going to use one based off of how the formula is written, as far as the function, or just whichever one's easiest to integrate. Because we know certain things, if you solve for x, might be easier to integrate than if you solve for y, depending on the function. So they look exactly the same, just one's all in terms of y and one's all in terms of x, and that includes the endpoints. So let's see if we got a couple of examples here. So let's move me just in case you want to see what's up here. But it says we're going to take the curve, y equals 1/3, and then it's times the quantity x squared plus 2 to the 3/2. And we're going to find the length of that curve from x equals 0 to x equals 3. So we're going to use the formula that's all in terms of x. So we already know what y is. Y is, or f of x is 1/3 x squared plus 2 to the 3/2. So what we need to do is we need to find the derivative of that. Okay, and that's going to be a power rule and a chain rule. So the 1/3 is there, and the 3/2 comes out front, so that gives me 1/2 out front, and that goes down to a power of 1/2, and that's x squared plus 2. And then it'll be times the derivative of x squared plus 2, which will be 2x. So this thing, when we multiply it out and kind of clean it up, the 2 and the 1/2 will cancel, so we'll have x times x squared plus 2 to the 1/2. Now that doesn't look very attractive, but keep in mind this thing says we're going to square that. So let's do that. F prime of x squared. So in that case, what we're going to do is we'll square x, so that'll be x squared, and we'll square the square root, which will knock it out. Squaring the 1/2 power will knock it out. So it'll be x squared from this first term, and then times x squared plus 2. And if we distribute that, it looks like it'll be x to the 4th plus 2x squared. Okay, so that might look a little intimidating, but that is what we're going to plug in for f of x squared. So let's set that up. So the arc length L will be the integral from 0 to 3, because that's the x powers, of the square root of 1 plus x to the 4th plus 2x squared. A little messy. Let's take a moment to try and clean up a few things here. Come on, Mr. Eraser. Okay, and we're going to integrate that in terms of x. Now that looks pretty scary at first because you're thinking, wow, there's some crazy stuff under this square root. How am I ever going to integrate that? Because I'm thinking u substitution, but let's take a look at this. This thing under here, and this is the way most of the arc length problems you are given will work, is a perfect square. You can factor that x to the 4th plus 2x squared plus 1 out. It'll be x squared plus 1, I believe, times x squared plus 1. So it has a perfect root. So this is really the integral from 0 to 3 of x squared plus 1 dx. Let's go ahead and save a little bit of room and integrate that. X squared plus 1 will be 1/3 x cubed plus x, and that's going to be integrated from 0 to 3. So we'll let x equal 3, and when we plug that in, we'll get 27 over 3, so that'll be 9 plus 3, so that'll be 12, minus, we're going to let x equal 0, which will give us 0 plus 0. So this arc length is said to be 12 from the way we calculated it. Let's write that 12 a little bit nicer. Okay, I'm going to pause and rearrange my things here before I do the next one. Okay, I'm back. So before I go on, one thing I do want to just kind of make sure we're clear on here is taking a look at this square root. I don't know if it's going to happen in every problem, but for a good number of the ones we try, usually something under there will factor and be a perfect square. It won't always be like a u substitution that we're used to handling when we have a complicated thing under a square root. So let's go to our next example. It is x equals y to the 3rd over 3 plus 1 over 4y from y equals 1 to y equals 3. So in that case, everything's in terms of y, which is great, no problem. So let's just see here. Our g function, which is in terms of y, is 1/3 y cubed plus 1/4 y to the negative 1. I just rewrote it. So let's take the derivative of that. So g prime will be y squared minus 1/4 y to the negative 2. And then we've got to square that for our formula. So g prime squared, this is going to be a FOIL. This is not like the last one. This is going to be a FOIL. So it'll be y to the 4th minus 1/4 minus 1/4. So that'll be plus, no, excuse me, not plus, minus 1/2. So when we do the first and the, when we do the outer and the inner, we'll have y squared times negative 1/4 y to the negative 2. So those y terms zero out, but you'll have a 1/4. You'll have that twice, so that'll be minus 1/4 minus 1/4, which will be minus 1/2. And then the outer term, the last term will be plus 1/16 y to the negative 4. Okay, so make sure you FOIL that out and feel really good about it. But let's see here. We're going to put this into our formula, which is L, and it'll go from 1 to 3, as the formula says, the square root of 1 plus y to the 4th minus 1/2 plus 1/16 y to the negative 4, all under the root, dy. So take a little moment to see here that here's a negative 1/2 and a positive 1. Those will combine. You may feel like rewriting this thing, but it's actually in the perfect order that we want it in when we look at it. So if I just rearrange it, we're still from 1 to 3, but we'll have the square root of y to the 4th plus 1/2 plus 1/16 y to the negative 4 dy. Now I'm going to write this out just like before. That is a perfect square under there. A little hard to see, but just get used to seeing this in this situation. So this thing under the square root factors into y squared plus 1/4 y to the negative 2 times y squared plus 1/4 y to the negative 2. So as far as a square root, we might run out of room here, we hope not. 1 to 3 of y squared plus 1/4 y to the negative 2. Okay. Now we still got to integrate that, so let's move my happy face up a little bit. So when we integrate that, let's change colors here just to get out of the rut. We'll have it as 1/3 y cubed. That goes up to negative 1, so we have minus 1/4 y to the negative 1, and that'll be from 1 to 3. So my integration gives me 1/3 y cubed minus 1/4 y to the negative 1, and I've got to integrate that from 1 to 3. So let y equal 3. And when we plug that in, 3 cubed is 27 over 3, so that is 9. And then it'll be 1/4 and y to the negative 1, so that'll be a 3 in the bottom, so it looks like minus 1/12, I believe. And then we'll have minus when we let y equal 1. So when I plug in 1, that'll be 1/3 minus 1/4. I'm going to use a calculator here. And I'm going to give it to you in decimal. Let me pause while I do it. Okay, if I'm not mistaken, this thing gives me 53/6, which is the same thing as 8 5/6 if you're trying to quantify that. So that's an arc length here.